think we're good. All right. Good evening, everyone. Welcome to another virtual star party brought to you by Glendale Community College Science Center Outreach Program. I am up at Mount Wilson in Southern California, and together with a small team of astronomers this evening. Everyone is scattered around the dome behind me. We are masked. I do have my mask for me to wear in a little bit, but I wanted to welcome you all here this evening for an exciting evening. We have 10 targets that we are going to try to aim for this evening. So if you are joining us for the first time, usually we look for either the moon or if it's above the horizon. Tonight we don't have the moon. But planets, if they're around, we're going to start this evening looking at Mars. And then we go on to what are considered deeper sky objects or deep sky objects. And these are objects that are outside of our solar system, so they're much farther out in space than any of the planets or the moon. And we're going to start with a couple planetary nebulae, maybe some double stars, a triple star. We're going to look at a couple of galaxies, hopefully we'll be able to see. But it is winter here in the northern hemisphere, and the seeing conditions are not ideal. So one of the things with astronomy is you're kind of at the mercy of the weather and the conditions. So the weather here is beautiful. It's a little chilly because it is winter. Right now we're looking at 7.5 degrees Celsius, also known as 45 degrees Fahrenheit. So we're all bundled up here. And so, you know, it's a little cool this evening, but that's okay. We love it. This facility is an amazing facility for an astronomer to be in. I love it up here. But the atmosphere above our heads is shifting around a lot. And what are considered seeing conditions are not ideal. So the images that you're going to see when I show you what we're looking at through the telescope are shifting around a little bit and not as crisp and clear as some of the images you'll find on Google. But these are real and they're live, and we're going to start with our first object tonight, which is Mars.
Do you want to show the telescope?
I do want to show the telescope before I get there. Now, the telescope is going to be there. So you can see me over here on your, I guess, right-hand side. I'm waving at you. I'm in the burgundy jacket. And we have some of the other astronomers around here. And before you can see in the middle of our image, we have got the historic 60-inch telescope here at Mount Wilson. Now, this was built a long time ago. It started to be built in the late 1800s, 1898?
1904, I think it started.
Oh, okay. So they were, the Mount Wilson Observatory facility started in like 1898, but this telescope started construction in 1904, and its first light was, I want to say, 1908. Yeah. All right. So it took 4 years to build this. It is an engineering marvel, and it is working as well now as it was back then. It is not the largest telescope in the world anymore, but when it was built, it was. And astronomers came from all over the world to observe here. I am lucky enough to observe here tonight. Now, Chris is going to point out a big red thing. I don't know if you can see it. Do you want to move the ladder over a tiny bit? Because the ladder is exactly in the wrong place. There we go. So this is our giant ladder, obviously, to get up to things. But there is, as Chris is pointing to, a large red cylinder. Well, I guess not that large, maybe the size of a can of pop, a can of soda. And that is a special camera that we placed on the telescope, and it is taking images of what the telescope is pointed at and sending them through the power of the internet to your screen, or it will be as soon as I switch over to that feed. but what I will let you know is you can see which way the telescope is pointing by which way the whole column is facing. In real time, it's facing west. So we're looking at Mars, and Mars is over in the western part of the sky. It's getting down a little lower, and it's looking through more atmosphere and through more of the murk, because we're looking through more of the LA skies, which aren't ideal for observing, let's be honest. All right, so I'm going to move over to the view that we have of Mars. So 3, 2, 1, hang on. There. Haha. I did it. We've got a new setup this week. Every week I come up, there is a new setup as we get new equipment and new toys to play with. New equipment. And right now, what you're seeing on your screen is Mars. And that dancing around that Mars is presently doing, that you see it kind of moving subtly around your screen, that is real. This is the image that we are getting. And what you're seeing is because Mars isn't out there dancing around like this, but the light coming through the Earth's atmosphere is being shifted around. So we have a situation similar, like if you've ever looked over the top of a barbecue or over the top of a hot road in the summer, where you can kind of see the shimmers, and what looks, what is beyond that barbecue kind of dances back and forth a little bit, like heat shimmer, heat waves. This is what we're looking at. And we may not think of the atmosphere right now as hot, but it's definitely hotter than outer space. And it shifts around. Even if it's cold, it will shift around. And so it's the shifting atmosphere that is causing the image that we're looking at to appear to shift around. And there's nothing we can do about that with the equipment that we have. This is just what we can see. So that's Mars, which isn't as crisp an image as you would have got, about a week ago, 2 weeks ago, with the Perseverance lander, when they showed pictures from the surface of Mars. Well, somewhere on that little orange blob is the Perseverance rover. So there you go.
Every now and then you get a clearer view, so there is a little bit of shadowing going on. So let's see what it actually is supposed to look like.
So we have Mars dancing around. One of the astronomers who is here with me this evening, Dr. Christopher Burns from the Carnegie Observatories, astronomer I know quite well since I married him, is beside me, and we are looking at what Mars should look like. And I'm going to go over and see if I can get a similar image so you can see.
Did you want to switch over to that knobs?
Will in a second.
Oh, okay.
I'm just going to see if we can zoom in. All right. Okay.
What's that feature called?
Mars. Hello. I have so many virtual screens here. There we go. All right. So what I am doing now is trying to get over to a different software so I can show you what Mars should look like. And Mars has just disappeared.
I think it's tracking. There you
All right, let's try this again.
go. Alt and tab at the same time.
Aha, Alt and Tab at the same time. All right, so I'm going to shift over to a software package called Stellarium. And this, you can see at the top of the screen, it says stellarium.org. This is a package that you can download for yourself if you want to see the same type of thing. And we have an image of Mars. And this particular image of Mars is very dark and very light. So they're really playing up the contrast. In real life, it's not quite as dark and quite as kind of brilliantly orange. But this is the exact view that you would see of Mars if our telescope gave a super, super, super crisp, clear view. It would look like this. So this is the side of Mars that is presently facing the Earth. And this little thing over here that says Phobos, that's one of the moons. And that's this tiny speck here. What you're seeing is one of the moons. I think that's what it is. I don't think that's dust on my screen. The moons of Mars are incredibly small. They're about the size of a small city, something like 12 miles across, 16 miles across. So we believe that they're captured asteroids, and they didn't form at the same time with the planet when Mars itself formed. But we have, Phobos is over there on another piece of software.
We're seeing it. If the next object that we're interested in is too low or not, we could explain why.
Yeah.
We have certain limits.
All right, so we're going to go back to the actual view that we have of Mars itself, which here looks less exciting. But we are thinking about going on to our next target. And our next target is an object known as NGC 1535, which is Cleopatra's Eye, right, Chris? Cleopatra's Eye?
Yes.
Is NGC 1535? All right, so astronomers have a lot of catalogs to catalog the millions, billions of objects that they've viewed out there in the universe. NGC is the new general catalog, new as of 1886, I believe. But NGC 1535 is also known as Cleopatra's Eye. Now, does it look a little bit like an eyeball? Maybe?
Use your imagination.
I guess if you use your imagination. It is a planetary nebula. So we're going to be looking at a few planetary nebulae this evening. And I guess it would help if I explained what they were. So a planetary nebula is the remains of a medium mass star. So stars come in different masses. There's a variety. There are low mass stars, medium mass stars, high mass stars. Our sun is a medium mass star. Our sun is pretty average. It's only the high mass stars that have the ability to go supernova, so never have to worry about our sun going supernova. It will not happen. But our sun, once it's used up all its nuclear fuel, will eventually go out. It won't go out with a bang like a supernova, it'll go out with a bit of a puff, like a planetary nebula. And the name is a bit of a misnomer. When astronomers in the 1700s started looking with better telescopes out into space, they saw these round, kind of greenish, bluish objects that were quite similar to the newly discovered planets. So this was in 1781, Uranus was discovered, and Uranus, of course, has this kind of bluish-greenish color. So they saw these other objects out there, and they thought, oh, it's another planet, because they didn't know. Once they discovered Uranus, they're like, oh my gosh, maybe there are hundreds of planets orbiting the sun. Not the case, just 8. But this planetary nebula, they realized was a nebula, which is a fancy word for cloud of gas and dust in space.
I'm going to turn the lights up so we can watch it move.
Oh, okay. I'm going to turn the lights on so you can see how the telescope actually moves, which would mean I need to go back to the inside of the dome. So you can see two things are happening here. The dome is going to be moving, and you can see that kind of red in the background, the rust colored up there. It's not actually rusty, it's just painted that color. And then the telescope itself is going to start moving. So where was I with planetary nebula? So once the sun uses up, or once a medium mass star uses up its nuclear fuel, there is nothing to really hold the star up anymore. So a star is any star if it has thermonuclear fusion in the core is basically the core exploding and sending a lot of energy outward, but gravity holding things together. It's a constant tug of war. If you don't have any nuclear fuel fusing in the core, there's no energy to kind of offset the gravitational collapse. So gravity wins and the star collapses. And in the case of a high mass star, this collapse is catastrophic, and then it's a collapse and rebound. That is a supernova explosion. But for a medium mass star, it's kind of a collapse and a poof. And it's that poof that we're going to look at. This is the Planetary Nebula.
Okay, so we're there? Oh, okay.
We're not quite there. We're getting there.
You can see that we're really far over, and the operator, Mr. Tom Minigini tonight, is being very cautious about, you go back so people can see.
Oh yeah, oh my gosh, I've never seen it that low.
Yeah, this is, this is very close to as far as we can go.
So if you can see the angle the telescope is at, it's kind of lying down that way. And usually we like it a little more upright. When it gets too far down, I mean, there are some limits to how far down this telescope can safely function. This is about at the limit. So there's a lot of caution happening in the moving of the telescope this evening.
All right, I'm going to bring the lights down since we've got to actually find it.
All right, so now we're back in the dark. Are you looking for... I'm going to turn over to the view through the attic camera. So the attic Horizon 2 camera is the camera that we have that is attached to the telescope. So it's not like looking through the viewfinder. We have to kind of set some parameters, and you can see there is a slider tab at the bottom that has like a little hump in the middle. I don't know if I can show you with my mouse here, but there's two parameters, two lines, a black line and then a white line that you can see Chris drag over to different places so that he can try and maximize contrast. We can also allow the camera to collect light for a longer period of time. So that's the exposure length or exposure time. And if you have longer exposure time, you collect more light, then you're more likely to see faint objects.
I think we're looking at that. So we're not quite there yet.
So with the telescope, it is automated, and you can set the coordinates. If there are any of my students out there, we just finished a unit on mapping the cosmos where I was talking about the right ascension and declination coordinates for stars. You can set the RAN DEC, which is short form for right ascension and declination, and then ask the telescope to slew to that setting. But you don't always get right on. So sometimes you have to kind of hunt around a little bit. Now, for those people who've never taken an astronomy course and don't know what on earth the right ascension and declination are, if you remember back to grade school when you did latitude and longitude, it's the same type of thing. So if you're going to try and map the Earth, you have a grid that you kind of superimpose over top of, a big ball. If you remember back to grade school and your teacher had this amazing globe on a stand, and they never let you spin it really fast, which is really what you wanted to do because that looked fun. I learned why teachers don't let you do that. I actually got a globe for my own kids, and they hit it so hard they knocked it right off the table because they wanted to spin it faster. So the globe broke. So I see teachers' point of view. However, if you look at that globe, there are lines that go from pole to pole, and these are the lines of longitude, and then there are lines that go parallel to the equator. So the equator is kind of the zero line of latitude, and they go concentric circles up toward the North Pole or down toward the South Pole. That's latitude and longitude. This may be ringing a bell for some of you, or not. If it's been so long since grade school, you can't remember, but I'm sure you got it. The lines of right ascension and declination are very similar. So we imagine everything kind of on a huge glass sphere, and then we superimpose these imaginary grid lines on this sphere, and then we map the stars. Because if we want to talk about where stars are, if we want to use a telescope and tell the telescope to go to this place, there has to be some sort of standard that is understood by all astronomers, and by all telescopes for that matter, or the software engineers who are writing the programs to run the telescopes. Whoa, that is a very bright white light. That is, should we go back to dome view? Oh, dome view is very dark. You can see me scratching my forehead. That's what happens when you wear a wool hat. Scratchy, scratchy. So this is the time where I need more filler. So we are looking for Cleopatra's Nebula. Let's go to Stellarium and see if we can find that. So I am actually going to head back to the Stellarium software package. That's what you're seeing now. This is the previous view of Mars. And I am going to search for Cleopatra's Eye Nebula. It was already set up for us there. Whoa, zoom out, zoom out, zoom out. Okay, so this, if you have not a great telescope, you're looking at this, it looks very much like a bluish, greenish blob that honestly looks a lot like Uranus if you're looking through a kind of a low power telescope. But with better telescopes, astronomers over the decades and over the centuries could zoom in and get a much, much better picture. And when astronomers first saw this, they're like, what the heck is that we're looking at? At the very center, that is the old core of that medium mass star. It's still really, really hot, and it is giving off a lot of light, UV light in particular, and a lot of blue-white light as well. So this is kind of the compressed old heart or core of the medium mass star. The area where thermonuclear fusion used to happen is no longer happening because there's no fuel left. And then this kind of outer bubble here is a lot of the outer atmospheres of the star that kind of got blown out into space. And it looks here a bit like you could kind of imagine it as a disk, and we're seeing it face on, like looking down at a plate on the table. But in fact, this is a whole sphere. So this is kind of an inner sphere or bubble of gas that is being pushed out from that white dwarf center. So the white dwarf is actually giving off, as well as light, giving sending out a lot of particles. And these particles, protons, neutrons, this make up the stellar wind. And the stellar wind is actually pushing this material to make this bubble. So this bubble is expanding over time. And in 10, 20,000 years, this whole thing will no longer look like this. All of these gases will have dissipated into outer space. This outer bubble is material that would have been ejected previously. It's had longer time to move out into space. So this is what we're trying to get as a view through our telescope. How are you guys doing?
Terrible. Well,
Terrible.
Yeah, it might be too far over.
Oh, it might be too far. Too dim, or it's too far below the horizon?
It's way over. This is the refractor, 30 seconds.
Oh, we're trying to do a 30-second exposure to see what we can do. So for the astronomers out there, and for those people following along, this is an object that is 9th magnitude. So the magnitude scale astronomers use to try and quantify the brightness of something, the apparent brightness of something. So this was something that came out, Hipparchus invented the scale, oh gosh, a couple of thousand years ago. And he said that the first class stars were the brightest ones, and you can think of them, they're kind of first place. And then second class stars, or second magnitude stars, they weren't quite so bright, so they're kind of second place in brightness. And with just your eyes, the unaided eye, or with glasses, I suppose, if you're using glasses or contacts, we can see as faint as sixth magnitude, so the stars that kind of come in sixth place. This is ninth magnitude. So this you would not be able to see from the least light polluted place on Earth. And having allowed your eyes to dark adapt for hours, you're still not going to be able to see this. It is simply too faint for the human eye to be able to see. This is why telescopes are like the astronomer's best friend, because they collect light and allow us to see the object in the first place. So we have the lights back on here in the dome. Where are we going next?
Oh, we're just gonna go to M42 because.
Oh, we're gonna go to M42, which is so exciting. If you know what M42 is, you can get excited now. This is the Great Orion Nebula. And let's go back to Stellarium so you have a bit of an idea of what it is you guys are gonna be looking at. So I'm gonna go over here into the search window, and M42, already there. And once again, wow, we are zoomed right in. Okay. Interesting.
We know we can.
We have some things that I didn't know were on. Okay, so what happened to all the stars?
Stars disappeared. Oh god.
The stars disappeared. Stellarium is acting a bit like a prima donna. I'm gonna have to say it is not behaving properly. This should be filled with stars. I may have to reboot Stellarium, but we'll do that in the background when we're looking at something. But over here, there is going to be the Great Orion Nebula, and as I zoom in, you'll have a better and better view of this nebula. Now, this is not a planetary nebula. Planetary nebulae are really quite small. They are produced by a single star, and they would be a few times the size of the solar system, maybe 100 times the size of the solar system. This Great Orion Nebula is thousands of times the size of the solar system. It is huge. And this isn't a product of stellar death, if you would. This is where stars are formed. So this is what's known as a stellar nursery. And we can keep zooming in and keep zooming in, but I think we're going to just blow out what we're looking at. There are 4 stars in this really bright region here, known as the trapezium. But there's gases that are glowing different colors, and there's also dust. So over here, all these darker areas, these are dust lanes. And dust obscures the view of what's behind. So if you ever have a dusty windshield on your car, you're like, oh man, I should have taken a Windex and a rag and like cleaned off my windshield before you go driving. So you have a crisper image. You can't see so well through the dust. There's so much dust up here on the right-hand side that you can't see at all what's behind this. This is called Interstellar Extinction, where the dust, the light from what is behind it, is completely extinguished by the dust, turned off, if you would. Absorbed, actually, by the dust molecules themselves. There's a little bit of dust over here in these dust lanes, but down here we have glowing gases. And one of the things that you will see in a lot of nebulae in outer space is the color red. Most of the universe that we know and we can interact with, the atoms and molecules, most of the universe, 80% of the universe, is hydrogen gas, and hydrogen, period. And this red color is characteristic of energized hydrogen and the light, the specific color of light that hydrogen gives off. So you'll see a lot of red glowing nebulae if you Google nebula, and the red that you see is due to hydrogen gas. Nebula, by the way, is the singular. Nebulae is the plural. It's a Latin thing. Yay for Latin. So this is the Great Orion Nebula. Now, I am going to go over and see what they're finding with the attic view, that is not a whole lot.
We're just centering.
Oh, you're just centering?
Yeah.
Okay.
Whenever we do this, we end up in a position which is not quite.
Yeah. The telescope is good. It will get you most of the way there, but then there's like the fine tuning. So in the background, you may hear some gears and some motors and things like that. That's actually slewing the telescope. And slewing is the verb astronomers have for moving the telescope from one place to another. So you can move it quickly. Generally, I think slewing is, well, no, it's referred to both fast and slow motion. But there's fine slewing if you're going really slowly and because you don't want to like overshoot and have to come back. Ooh, you got it?
Yeah.
Can I join you?
Oh yeah, no.
All righty. Let's go back to the attic view and see what we have. Oy, oy.
We're still in motion.
Okay, they're still in motion. And you can see those 4 bright stars that I told you about. They're kind of bleeding across the CCD chip, or the CMOS chip for this camera.
Okay, you don't necessarily want to be on these because it's forever bright. We can do it once we're there. Stay right there.
All right. This is looking much better. We've got nebulosity. We got some stars. This is looking good.
There it is. There we are. We're just blowing out on the central stars.
Now, this YouTube live stream does have a chat feature. If you have any questions, please put them into the YouTube chat. There is a delay between when I say anything and when it ends up on YouTube. So there could be up to a 30-second delay before I can see what you've typed and then get back to you with answers. But if you have any questions, please throw them into the chat because I would really love this star party to be a little more interactive as opposed to me just talking for 2 hours, which is exhausting more for you than me because I'm kind of used to it. But I'd love any questions that you have, especially if there's any middle schoolers out there who have questions, or any students for that matter. But I'm hoping there's a particular middle schooler who will be here this evening. Someone who's perhaps a little frustrated with math class and needs to have a dose of science and math that is not a typical classroom.
Pretty good for the nebulosity.
So we can count. That's math. 1, 2, 3, 4. 4 bright stars in trapezium. And countless other stars out there as well. I can try counting them. 1, 2,
All right, I'm going to try doing the old live stacking.
3. Ooh, okay.
Big boys.
Well, so that way we can.
So what Chris is going to try and do now is stack the images. So the way the camera works is it takes a picture, sends it down the cable, because we've got this hard lined in to the computer, and then the computer sends it off to live stream and you can see it. But there is a feature in the software that came with the camera whereby you can take a picture and then hold it and then take another picture and then stack that so that you're actually getting twice as much light. And then you can stack a third picture and a fourth picture. And if you stack the images, you may be able to see better color, higher resolution, and a crisper image than just what you can see with one single picture. The software also, you can set parameters that you're like, okay, well, if the atmospheric seeing isn't great, then we can kind of ditch this and then ditch the one picture and then stack the pictures that were good, that were taken when the atmosphere was particularly still or calm for that split second, and it will take a picture and then it will only keep the best pictures to produce the image at the end. And I can guarantee you that all those fabulous pictures you see on the Hubble Space Telescope webpage and other web pages out there are going to be stacked pictures, and they're probably also a little enhanced with the color. So the color is real, but someone's gone in with a computer program and just kind of amped up the intensity of the color just to make it a little more impressive. So it's all astronomically accurate, but it's just got a wow factor.
You can already tell that the seeing here is a lot better than it was last time.
Yeah.
We can distinguish the
Yeah.
stars.
A couple of weeks ago, we were up here, and those 4 stars looked kind of like one big misshapen blob. So that's what you get with bad seeing. You get stars that seem to dance around so much that you can't tell that there are 4 individual stars. It just looks like one big messy blob of light. But now we've got some fairly decent seeing. A bit of steady sky there.
It's not bad. It's actually not bad.
Yeah.
Let's keep it going.
Yeah. So one thing we can try is we can bring over that view into there.
Okay.
So for the first time,
This is so exciting.
we have some people up here. Can I say your name?
Sure.
Richard Bell has a telescope, smaller telescope, a refracting telescope, which is 5 inches in diameter. And it's it's remotely controlled, and it's in a roll-off shed up here on the mountain. And he's got it so that we can actually look at it remotely, just like we're looking at the view through the 16-inch remotely. So I'm going to try dragging it over so you can see what it looks like through his smaller telescope, but it has a wider field of view.
All right, so let's get back to that.
Let's see if this works.
All right. So by dragging it over, we have 2 monitors, and he's just literally dragging the screen that shows it out. That's beautiful. So Mr. Richard Bell is one of the intrepid team of astronomers we have up here, and he's been working on this lovely refracting telescope that is completely set up to run remotely. Right, Richard?
Yeah, I can run it from my house.
Yeah, so he can run it from his house down the mountain. That if he doesn't want to make the hour-long drive to come up here, then he can just get on his computer and say, okay, dome or a roll-off shed is a shed, kind of like a garden shed you'd have, but the roof itself is on rollers, and it physically rolls off the top at the touch of a mouse button. And then there's cameras on the telescope. Everything's controlled by a computer in the roll-off shed, and everything can be controlled from kind of down the hill. This is beautiful.
I'm going to try and zoom in to the same level that we're
Yeah.
at the 60-inch, just to have a comparison.
Yeah, so we're going to go back and forth between this 5-inch refractor and the 60-inch.
You can't keep up with that.
Okay, so is that still too big? I don't know. Also, we're probably flipped around.
You can see them going back and forth.
Let's see. How about flip back and forth? Flip horizontally on this. There's got to be a way to do that. Effects.
Is it not the same view? I thought it looked like the same view.
Did it?
I think so. Yeah. Oh, maybe not.
Yeah,
Zoom in more.
this 16-inch also is flipped
Yeah.
horizontal.
And a refractor versus
So you can see that the 60-inch does have the advantage of better resolution. Typically, the larger the telescope you have, either mirror or refractive lens, the better resolution you have. So astronomers just want bigger telescopes. You have more light gathering ability and more resolution ability. So this is a really good example of that. A 5-inch in diameter lens versus a 60-inch in diameter, that's 5 feet, mirror. You just get more light gathering with a larger surface area and a higher resolution as well.
Now, the other thing
But
is...
it's still a really pretty picture.
Yeah, it's got 30-second exposure, whereas we're doing 1-second exposures.
Okay.
So we could go and do a 30-second exposure on the 60-inch just to see how that looks. complex.
A 30-second exposure.
Yes, explosion.
Exposure.
That's right.
I was about to say that's going to completely saturate
We're gonna get a
where the
30-second
stars are.
Explosion.
Oh, this is
Let's do 10
this is
seconds.
a
Let's not
exciting.
get crazy, just quite yet. So I'm gonna do 10 seconds.
This is our Tuesday night excitement. Woo! 30-second exposure. I might have to have a sip of my tea to calm myself down. Oh gosh, it's gone cold.
Hold on. I just have to... See, unfortunately, this software does not auto scale for some reason.
They look like car headlights.
Oops.
Whoa!
That didn't work.
What the heck was that?
That was the stack getting completely wrong.
Oh, the stacking of images is the software just went.
Yeah, it did not work. Let's see if it figures
Nope.
it out this time.
Oh, one of my students made it. Hi, Nanette. I just finally looked at the
20
chat.
seconds now.
The chat needs to like make noises at me. I'm so glad that you could make it this evening.
Color balance goes really
So I have, oh, how many students have I got this semester? 60? 60 odd students this semester? Some of who are coming this evening. More will come over the course of the semester because they have a project to do, watching a star party.
here. We do 600. That's kind of getting there. Well, maybe that's too much.
Wow, that's really kind of blowing out trapezium.
Oh yes, there's no that. So
But you
that's
can
the-
definitely see that there's some color in the nebula down here. And almost you can kind of feel that it's kind of fluffy, like it's not flat, that there's parts of the cloud that are a little more dense, and there's texture, if you would. Not that you're going to feel anything if you go out there, but because it's not small, we've got, oh gosh, I don't know how many thousands of light years. How big is the Orion Nebula? Let me have a look at my.
That's it. No, it's not it.
No, it's flipped horizontal.
Nope. Hang on.
So flip.
Do. All right, so the Orion Nebula. We need to know.
Cameras could be rotated.
It
different
can
ways
be
all the
observed naked eye, although that's really challenging.
Binoculars will work.
Binoculars, you can see it easily with binoculars. So, if there are any of my lab students here, you guys have been looking at Orion, and this is the below Orion's belt, and it is something that you can see. You know where to look. From LA skies, though, I think binoculars would be very, very helpful. So, in my database about this object, it says the Mayans of Central America had a folktale that suggests that they knew of the Orion Nebula. Well, that's not surprising because you can see it naked eye. Blah. But despite being visible naked eye, the nebula is not mentioned in any known historical records before the invention of the telescope. Neither Ptolemy nor Al-Sufi noted the nebula, even though they both listed patches of nebulosity elsewhere in the evening sky. Huh.
Feels like I should.
It is not telling me how. Oh, the apparent size. Nope, I don't want apparent size because being at 1,400 light years away, it's gonna be apparently very small. I want an actual physical size. And my database is letting me down. Oh, I am sorry. I just didn't read far enough down. M42, the Orion Nebula, is located at a distance of 1,350 light years, with an uncertainty of about 2%. So this is where significant figures, Annette, come into play. So you get plus or minus a little bit. So 1,400, 1,300, somewhere along those lines. It's estimated to be 24 light years across. I thought it was just like 2 light years across. That is gigantic.
It's huge.
Light takes 24 years to get from one side to the other. And if you're going to talk AU, there's what, 100,000 AU? 200,000 AU in a light year? Something like that?
I should know these things. I really
It's
should
just
know
unit
these
conversion.
things.
This
I
is more
know.
math.
They're such on different scales, I just never worry about those.
Yeah, I mean, an astronomical unit is very useful within the solar system, but it's not useful at all when you get to things outside the solar system because space is so big that, you know, it's just like using centimeters to measure the different, or inches to measure the distance between LA and New York City. It's like, why are you using that unit? That's a really silly unit to use. AU to other, you know, nebulae or whatever. How we doing?
Good. I'm going to bring Richards over again, just to point
Richards definitely has a better color. I don't know what that is attributable to.
I think our color balance has gotten messed up for some
Yeah, maybe our color, because it's not supposed to be that blue, what we're looking at with the attic camera.
Yeah.
He's less encumbered by atmospherics than 60.
Yeah. So the other thing is, if I bring it back,
Okay, here's the 5-inch telescope view.
so one thing you notice is that you can see the gas really, really well, but the stars don't pop out quite as well. So
Huh.
let me bring back the other one.
Oh, yeah.
So you can see a lot more stars.
Yeah.
And I believe that's because of the difference in the optics.
Yeah.
Well, yeah, not only that, but the F ratio, I think, also affects your ability to
16
see.
versus 7, yeah.
Yeah, it's a slight difference. So these the 60-inch was extremely good at finding faint, small things rather than faint, large things.
Yeah. I guess you could say the optics of the telescope is kind of like the engine. So some people buy telescopes by how nice they look. That is not a good way to buy a telescope, right? You know, not a good way to buy a telescope, I can guarantee you, is on the box where it says magnifies 200 times. If you're buying a telescope by how well it magnifies, do not buy that telescope. Or if you're buying a telescope that is selling magnification only, don't buy it because you're just going to magnify a blurry image. You want to know the optics and how well a telescope can resolve the fine detail. If it's going to be a big blob or it's going to be for individual smaller blobs. For telescopes that you would buy at Target or Walmart, much better spending your money on a good pair of binoculars. That the optics are kind of like the engine in a car. I mean, you can buy a car on, you know, what color paint it is, or I suppose how much you can fit in the trunk, but you got to know if the car is going to go anywhere. Is it going to go? Is it going to stop? That kind of thing. So there are things that are more important than magnification for a telescope. Magnification you can change when you change eyepieces.
Okay, so we've been stacking and we've got 260 seconds.
260 seconds.
So now I'm gonna reset it so you can see what one.
Okay, so we're having a good look there. Now you're going to go reset it.
Oh, you want me to save it? Okay, I'll save it. I think I used to do this. Load as on screen, file type.
You guys are getting a behind the view look at all
Wherever
the
it goes-
software.
Oh, okay.
Save somewhere on the computer.
Oh, I'm sorry, you guys are seeing all this. Okay, so we saved that, and now we're just gonna reset.
So I'm just looking back at the chat. Hey, Edwin, glad you could make it. We are looking at the Orion Nebula. So this is the Great Orion Nebula. It's one of the most famous, and it's the constellation of Orion. Now, Orion for you guys down in Glendale or down in the LA basin is going to be in the south, a little bit to the west, up kind of due south. And Orion is a really famous constellation. It's got, it's kind of like a big rectangle with 3 bright stars going through the middle. And the 3 bright stars going through the middle are the belt stars. Are we going, did you save that?
I did save it.
Okay, are we back to 1 second?
Well, at this point we're at 40 seconds. Here, let me
40 seconds.
reset it.
Reset to
So
1
this will be
second.
back to I think we're at 10 seconds. Yeah, 10 seconds. So it should look grainier.
Yeah, it doesn't have quite as smooth a texture of the nebula. So let me head back to Stellarium just for a minute to show you kind of where we are. So here we are in Stellarium. Oh, we can't. That's right. Because Stellarium has managed to make all the stars disappear, which is so frustrating. So I'm going to go back here to the attic view. And while we're doing that, and you guys are looking through the telescope, I am going to go and see if I can't just quit Stellarium. Hello. Quit Stellarium. And then open it again. Just, do the magic. When in doubt, reset.
So we are going to start slewing to the next object.
Okay. So Stellarium is working again, but I am now not sure that we're going to be able to see it. So let us go to Stellarium. And we can. Awesome. All right, so we can say goodbye to the attic camera and our now somewhat blurry view of the trapezium within the Great Orion Nebula. And I'm going to talk about it within Stellarium for a little bit. And they're going to slew to the next object. Now, where did the iPad go? What's the next object? Oh, the Clownface Nebula. Awesome.
I can also turn the lights on so that we
That's
can
okay.
see the
Yes, you can
telescope
turn the
view.
lights on if you like.
2392.
2392. Why? Excuse me. And edit. Take that off.
That does not like that.
All right. Hang on. So we're back in the dome view. For those of you who may be just joining us on YouTube Live, I'm over here on your right-hand side. And here's a giant telescope. And the dome is moving and the telescope is moving. We are now going to slew the telescope over to the Clownface Nebula, which to me doesn't look anything like a clown, but also known as NGC 2392. So let's go back to Stellarium though, because I wanted just to finish up with Orion. So over here you can see the constellation of Orion. So here is facing south, this S is south, and if you look, there's kind of a subtle horizon here. And this is a program called Stellarium. And with Stellarium, you can kind of check out what you think you may be looking at. So Orion is over here on the left, and all of the constellations are up there. I can actually put the constellation wires on, which are the kind of historic stick figures, if you would. So up here on the left-hand side toward the top is Leo, the lion. And here's the backwards question mark of Leo. This is the head and the mane of the lion. The lion's kind of lounging out, and then the tail of the lion is somewhere down here. That's very exciting. These two stars over here, I'm sure you would recognize them as a small dog.
Oh, there it is.
Or not. Over here we have Canis Major, the large dog, and Sirius is the brightest star in the constellation of Canis Major. But Betelgeuse is, and Rigel, these are stars within Orion. So Orion is over here. And to give you a little stick figure, or not the stick figure, kind of the schematic we have, I'm going to head kind of over to Orion here. Actually, it's a little more than just a bit west of south. It's now actually between southwest and west. So this is Orion. And I'm going to turn off the stick figure and kind of point out the rectangle of bright stars. Betelgeuse, Bellatrix, Rigel, and Siph. And then Alnitak, Alnilam, and Mintaka. I believe, I don't think Rigel was chosen by any of my students. But all of the other bright stars in Orion were chosen because my students get to choose and learn about their own star. The Great Orion Nebula is here. So if we zoom in here, you can see a similar view. And as we get closer, you can see other things pop up. HIP is a Hipparchus catalog. Yep, so the trapezium is over here. And why are things moving on Stellarium? Because I didn't pause the rotation of the Earth. Is the nebula actually moving through the sky like this? No, the Earth is rotating. But let's back out, because I'm going to give you a sneak peek of where we're going to, which is, it's the Clownface Nebula, right? NGC 2392. Okay. NGC
Something weird's going on.
2392.
Oh, we're stacking. Never mind. We're just stacking.
Ah, there we are. Whoa, zooming way in. Okay, I know what we're looking at. Again, something that you're not going to be able to see without the help of a telescope. So you can see there's Orion over here. This is going to be up here. I think it's in the constellation of Gemini. So let me throw some lines on. Yeah, Gemini's over here. Gemini the twins. Procyon, the small dog, and its other star. Capella within Auriga. Aldebaran down here within Taurus. All sorts of good stuff. But let's zoom in to the Clownface Nebula, and I will tell you why I don't think it looks like a clown. I mean, you probably have an idea in your head of what clowns look like. Is that what you're thinking of for a clown? I doubt it. But we do have a bright white dwarf at the center. So if you're here earlier when I was talking about Planetary Nebula and white dwarfs, you may remember that a white dwarf is the old core of a star, a medium mass star that has gone out. So it's used up all its nuclear fuel, and there was nothing to hold the core up. It collapsed, and then it puffed off its outer layers. So this is basically what we're looking at.
So we're good to go.
So I am going to go back to the attic view. Are we ready for the attic view?
Yep.
Yay! Oh, look, there it is. Oh, it almost looks exactly like Stellarium. Oh, that's so nice. And I'm trying to zoom in with my mouse and clearly not having any effect because we're looking at the telescope. So Chris, my husband, is over a different computer controlling the software that the camera on the telescope is looking at. I'm kind of at the broadcasting command post over here. We have 6 screens? No, only 5 screens. And all sorts of fun stuff happening up here. And it is really beginning to get cold. Oh. Yeah. Okay, I was about to say there is a draft coming in. It's still above freezing. It's 6.7 degrees Celsius, which is 43.9 degrees Fahrenheit. Wow, it's dry. Humidity's at 10%. 10%, yeah. Okay.
It's a dry cold.
It's a dry cold. It's just cold.
That doesn't work that way. Dry heat might be, but
So this is where I get my balaclava. And if you don't know what that is, it's kind of like a, I suppose the best thing to say, it's that it's what the cartoon bank robbers wear. They put it over their head and only their eyes are kind of visible. Goes down over their mouth and their nose and their neck, and then you put your hat back on top of it, and this is how you stay warm when it's really quite cold. But I'm going to kind of poke my mouth out so I don't quite look like the iconic bank robber of the 1960s cartoons. I don't know if the middle is the clown's nose. Maybe if the clown doesn't have any eyes. So there's a comment in the YouTube chat saying the middle of the Clownface Nebula could be the clown's nose.
I think at the bottom there's something that almost looks like a mouth.
Maybe, because it's not quite as spherically symmetric. It kind of is a little lopsided, which can happen when, there are jets of material being spewed from that white dwarf at the center in an uneven fashion. You know, explosions are never symmetric in all directions at the same rate. And this is basically, you know,
This temperature? No problem. Go for it.
Go for 30 seconds for it?
No, 30 second, or 30 cool.
Oh, minus 30. Oh,
Yeah.
All right, sure, why not? Well, let's let it get to 20 first and then we'll...
oh, you forgot to put the cooling on for the camera?
No, we've just been bringing it down slowly.
Oh,
Get it confused.
so this special camera for the telescope is cooled. It has electronic cooling,
Electronic cooling.
because if things get really warm, then that can interfere with the data that gets transmitted. So we want to keep everything nice and cool. One of the reasons that the dome is not heated, because you may be wondering, well, can't they afford heaters up there at the telescope? We absolutely can. But if we heat the base of the telescope, then it's just like barbecue. You get all the heat shimmering, and that makes for terrible atmospheric seeing. This would be dancing all over the place, and we wouldn't get a good image at all. So, yeah, we don't want to do that. So sometimes big telescopes have what are called warm rooms, where the astronomers sit in a room, kind of in the base of the observatory facility, which is isolated and very well insulated so that the warmth doesn't leak out. And they can sit there at their computers and monitor the telescope from a computer. But many amateur setups, with the exception, I guess, of Richard's, you have to be on site to do that. Certainly the telescopes we have at the college where I work you have to be on site. We do not have them remotely controlled. Although there is a push now that everything seems to have gone remote in the last year, there is a push to have the ability to have remotely controlled telescopes. So that's kind of exciting. But yeah, it's cold in here.
We talked about what the white dwarf is and all that sort of stuff, because I can give you a break if you want to stop talking.
The white, well, you know, Chris, you can absolutely take over because my tea became stone cold, so I'm going to go make myself a cup of hot chocolate and warm up a little bit. Oh, hang on. Gotta move from my post.
Okay, were there any outstanding questions? Nope, clown's nose. All right, so one of the things that's interesting about what we're looking at here is this is at the opposite end of the evolution of a star. Before, we were looking at the Orion Nebula and we were seeing stars that had just been born. This is a star that has died. And in stars like our sun, they make their light by converting hydrogen in the core of the star into helium in a process called nuclear fusion. And eventually, a star will run out of hydrogen to turn into helium. And at that point, it starts to go into its final stages. And it will puff up and become a red giant. The heat on the inside will go up, and then it starts to fuse helium into heavier elements, including carbon and oxygen. But eventually, it runs out of those as well, and if the star isn't big enough and it doesn't get hot enough in the center, then it's kind of doomed. And what happens is the outer layers of the star become unstable, and they start to puff out into outer space. And that's what you're seeing as this sort of ring that's surrounding the bright center, and that bright center is the leftover material in the core, carbon and oxygen, and we call it a white dwarf. And gravity would really love to compress this thing down to nothing, but it turns out there's a principle of quantum mechanics of all things, and electrons can't be squeezed together into the same place. Quantum mechanics says, no, you're not allowed to do that. And so what's actually holding this star up, keeping it from completely collapsing on itself, is actually quantum mechanics, quantum effects. And if that's all there is to it, if that star is just all there by itself, then it will just spend the rest of its life cooling down. It will get dimmer and dimmer. That gas cloud that you see, the smoke ring will expand into outer space and it will slowly dim away. But sometimes these white dwarfs have a companion star or something close by, and it can donate material from one star to the other. The gravity of the white dwarf can pull the material of a close by star onto itself, and so it can gain mass. And as it does so, the heat on the inside of the core gets higher and higher, and eventually it can get so high that nuclear fusion turns on again, and it will start fusing the carbon and oxygen into heavier elements. But because of the way this star is put together and because of these quantum effects that are going on, the star can't adjust to this increase in temperature. It can't expand and cool off. And so the temperature goes up, the fusion rate goes up, the temperature goes up, the fusion rate goes up, and it's this runaway process. And in only a few seconds, the whole thing converts all of its carbon and oxygen into all the way up to things like nickel. And it explodes, and this is what we call a type 1a supernova. And that's the sort of thing I study, which is why I went on and on and on about it. And it looks like our stacking algorithm is really confused because, as you can probably see, these little stars seem to be appearing all over the place. And that's because between each exposure, the software tries to figure out how to stack these things together, and so it'll shift it up and to the left or down to the right to try and compensate for, imprecise motions of the telescope. But clearly it got it wrong, and so we've got stars where there should not be any stars. Yeah. Okay, so the other thing we can do is, just as before, we can show you what the view looks like through Richard's telescope. So I'm going to go over and pull that over. Oh, actually, first we're going to try a 30-second exposure just to see what that looks like. So let's turn the stacking off and go all the way up to, oops. Oh, that's okay. No, I turned the stacking off.
They said that it was going for here, but I don't know if
Of course,
you remember. It's been a crazy year. Okay, I have to find somewhere.
So if you're still watching, what we're doing is we've increased the exposure time to 30 seconds. So in another few seconds, we should see what that looks like, but we'll have to reset. Oh, question. What is the difference between a nebula and a supernova? Is a supernova the process of it dying? Okay. Ooh, look at that. That's much better.
That is better.
You want to adjust try adjusting the levels and see if we can get it a little bit less blown out. So to answer your question, the difference between this planetary nebula and a supernova is just the scale of the energy involved. So this, what we're seeing right now, this is not a supernova. This is the other outcome that these stars have, and it's a much gentler process. So the gas that's coming off the surface of that star is going, hundreds of kilometers a second. So it's fast, but it's not crazy fast. Now, if you have a supernova, and let's say not a type 1a supernova like I was describing before, but what we call a type 2 supernova, which is when you have a massive star. And this is a star that can keep on burning carbon, it can keep on burning oxygen, nickel, all the way up to iron. And when it gets to iron is this magical element. If you try and put two iron or iron and something heavier together, if you try to fuse iron, you don't get energy out of that, you actually lose energy. And so we often refer to iron as the star killer, because once you get iron in the core, the star can no longer produce nuclear fusion at the core to keep it up, and the whole thing, the whole surface of the star comes crashing down, and that causes a supernova, and that's a huge explosion. And then you're talking about the layers coming out in thousands, tens of thousands of kilometers per second, so almost a significant fraction of the speed of light. So it's a much, much, much more explosive, much, much higher energy. And that's the fate of massive stars, huge stars, things that are like, 20, 30 times the mass of our own sun. Our sun is a pretty typical sun. and it will end its life as one of these, which is a planetary nebula, which is, you can think of as almost like it's not really an explosion, but its layers do go out into outer space, but at a much lower rate. The energy just isn't quite as much. And Barbara just pointed out the supernova is an explosion. The nebula is dust cloud. Oh yeah, actually I should have said that. A nebula is just any name we give to something that's cloudy. It's fuzzy, cloudy. If the astronomers of old did not know what it was, but they could see it was kind of fuzzy, they would just call it a nebula because it was like a cloud. So some nebulas, like this one, are planetary nebulas, the ends of stars. Some nebulas are like the Orion Nebula that we looked at before. That's the birth of stars, the cradle of where they were born. And some nebulas were called spiral nebulas, and those are actually galaxies. So nebula is kind of this catch-all term that we have for back when we didn't really understand what all these different things were. Okay, if there's any other questions, we can probably move on to
The next object?
Oh, I was actually going to put Richard's view of this on.
Yeah.
Interestingly, that looks a lot better than it does on the screen. So let's bring up if you can bring up the faint bits a bit more.
White point or dark point?
I think it's the light point, maybe? Bring it up. Sorry, the other way. Sorry, maybe bring it down. Let's see. Yeah, we're starting to see it a little bit better. So it's interesting because we see the best view in our own computers up here, of course, but by the time it gets converted to a video and sent down to YouTube and YouTube does its own thing, the picture might not be as great. But hopefully you can see that there's more than one shell going on here. There's an inner shell and there's an outer shell, and this just goes to show that this is not just a singular event. These stars, at the end of their lifetimes, they can go through episodes of expansion and contraction, and they can send off their atmospheres in bursts. And so you can see these sort of shells going out. Okay. So next, I think we were going to do a double star, the triple star, Zeta Cancry. Oh, it's right here. So, I wish this thing wouldn't lock up. Although it does seems to be able to tell what I am. Yeah, so Zeta Cancry is our next.
Okay, so I'll
Yeah.
get that going and you can show Richard.
I can try.
Okay.
Are you gonna
So
try this
we are
one?
going to go back to the dome view. Jenny, would you like to turn the lights on?
Or do you want to drag over the other one?
What's that?
Did you want to drag?
Oh, right. Actually, hold on, Jenny, hold on. As I said, well, we're going to move, we're going to show you Richard's view, because, he's proud of his telescope.
Oh.
So that is the view of the same nebula through his 5-inch refractor.
Can you grab those windows, Rich, and move them over?
Yeah, I can show them that.
To show them the actual telescope and
It's gonna get very bright.
Oh,
Yeah.
yeah, let's turn, you can stop the attic.
do you want to just,
Yeah.
But now I've lost it. I lost my.
Oops.
See if I can get it. Where are you?
it should just be under.
No, it's got to be under this one. It's on this one right here. Nope. Come back.
We're fighting with multiple displays. There we go. Okay. So what Richard is showing you here, this is a live stream from his roll-off shed where his telescope is currently pointing where it's supposed.
That's the telescope there.
Yeah.
It does come up, I think. We're just waiting for it to.
Whoops.
Whoa.
What happened?
That's just a video.
Oh, okay. Sorry.
That's just.
And so when you have one of these remote telescopes, it's really important to have a camera there because you got to make sure that the telescope is in good health, that a bear doesn't come in, and the other thing, of course, you can see right back here. I don't know if you can see our mouse moving across in
think
here.
I
Yeah. Oh no, I think Richard, can you use your mouse and circle Los Angeles?
Los Angeles is over here in the corner.
Okay, or the whole LA basin.
Pollution.
This is Orange County over here. This is Monrovia down over here. and it goes all the way up toward Big Bear. And
Right.
all the way out that way.
So the point we're trying to make is this is the reason we don't do research grade observations with these telescopes up here anymore. We do have what's called the Chara array. That's a bunch of telescopes. I think there's 7. Is it 7 now? Or 8? 7. There are 7 smaller telescopes, but they are combined to act as a single large telescope, which gives them incredibly high resolution imaging of things like stars. So they can actually look at the surface of a star and see star spots on stars that are not our sun, which is really cool stuff. And they do this because they're looking at relatively bright objects. This technique of combining these telescopes together, called interferometry, works on very bright stars. And so they don't have to worry about the light pollution to do their science. But to work with something like the 100-inch telescope or the 60-inch telescope, we really are fighting quite a bit of background. And one thing you may have noticed when we compared Richard's view to the view through the 60-inch is that the background light, the sort of level at the back that you see, was brighter. And that's because the 60-inch, being a larger telescope, is going to see more of that background. And so it really kills you. And so that's why back in I think as early as 1925, folks at Carnegie realized that they would no longer be able to build bigger and bigger telescopes on top of Mount Wilson. And that's because they started introducing gas lights in Pasadena. Yeah, so we're gonna go to webcam, I guess? Yeah, okay. And so they had to make a decision, what are you gonna do for the next big telescope? And what they decided to do was move to Mount Palomar. And that's the 200-inch telescope in Mount Palomar, which is close to San Diego. And there are darker skies there, although San Diego get pretty large too. And so now Carnegie, which is the institution that used to run Mount Wilson, we now have our telescopes down in South America, in the country of Chile, where there's lots of mountains, also on the west coast, so all the great conditions that made Mount Wilson such a great place to do observations exist down there as well. And they are happy to rent us, no, we actually bought did we buy the land or did we rent the land? No, Las Campanas. We own land. Okay, so we purchased the land at Las Campanas Mountain. So that's Las Campanas Observatory. And we do most of our research grade observations down there now.
Remotely at the moment.
Remotely at the moment, because there's only a few people on that mountain running. We have 2 telescopes running at the moment. And well, that's the way it works. That's the way we do it, because we can't go down there yet. But normally we do like to travel down and be with the telescopes when we're doing our observing. All right.
You know what? We could do a walk around the telescope.
Sure, we can do a walk around the telescope.
roaming
Why not? Yes, please. Can we have the lights?
Lights.
Okay, now we're going to try and do this, and hopefully we will not get all kinds of feedback when we transfer over.
I think we
So,
figured out how to do it.
I think we figured it out.
All right, I'm gonna come back here. And I have to get the gloves off so I can manipulate the computer. Oh, my hands are cold. And let's see if we can get this working.
Okay, I'm going to start talking. There we go. Okay. Is the audio coming through? Can you tell?
I cannot.
Go to ops. It'll tell you. Hello, hello. Yep. Okay.
Audio's coming.
All right. So we can look around and see where the telescope's pointed. Back down again. So I think you probably saw this stuff before. And Jeff, if you'd be so kind as to get a flashlight so that we can look at the bottom. I think I had a flashlight over. You can really tell we're professionals here. oh, it's in my pocket. That's where. Okay. And you'll have to push the top button and
Thank you.
hold it. There you go.
Got it.
Okay. We're ready now. So the bottom of the telescope has a mirror. And so what we're going to do is we're going to go underneath and have a look in here. How's the look, Jenny?
See?
Okay. So as you can see, it's green. And the story you often hear is that that glass is recycled wine glass, and that's why it looks green, or wine bottle glass. But really what's going on is it's just a really very thick piece of glass. And when you have a thick piece of glass, you kind of get this green tinge. And the surface, the top surface of the glass is aluminized. So there's a coating of aluminum up there, which makes it reflective. And what you're seeing at the bottom, it looks like there's stuff kind of in the glass, but that's just a reflection of the support structure that's holding the mirror up. And you're seeing it through the glass and reflected off the aluminum on the top side. Okay. And I don't know if we mentioned it, but that's 60 inches across. And that's why we call it the 60, thank you, Jeff, the 60-inch telescope. Now, this mirror is parabolic and it acts like a lens, so it focuses light. So the light will come from outer space through this shutter and down the tube. It then bounces off this and starts to focus and then heads back up. And then at the top, I hope you can see, there is another mirror. So the light then strikes that mirror, bounces back again, down, and you can't see it from this vantage point, but there's a third mirror just hovering above the primary mirror, which is at 45 degrees, and it sends the light out the side to here. And if you guys were up here with us, which is the way we normally like to do our observing sessions, you would have an eyepiece in there. Get the really big one with the handles. So Jeff is going to go get an eyepiece to show you the kind of eyepiece that we put in our telescope for your viewing pleasure. However, because we're doing this remotely, we cannot bring you up here. And so instead, we have this camera, which is an Attic Horizon 2 CMOS camera. Okay, and here is the eyepiece. This, and actually if we point it at Tom,
Oh, there you go.
and he gets in the right location, you can probably see him upside down. Maybe.
Maybe.
It's hard to see with my camera.
I can't really tell either.
Not enough effort.
So if any of you are amateur astronomers, I can tell you that this eyepiece is a 6-inch eyepiece. Sorry, 4-inch eyepiece. Sorry, my mistake. And as I said, it would go up there in place of the camera so you could look through it. And oh yes, and that's our focusing knob, which allows us to focus. Now, in this case, it's focusing the camera. So we're not going to touch that because that would make other people very angry with us because they took all that time to focus their telescope. Are we at our location or should I keep going? Okay, so we think we are. Okay, we're going to go and turn the lights out and see if we're in the right place. So I'm going to mute.
Okay, I think we are back to regular. The lights are off. We're gonna go and have a look at Zeta Cancry. This is a star system in the constellation of Cancer, and it has various traditional names. We're not quite sure the pronunciation. It's either Tegmen, or Tegmeni. They give all different options. It's about 83 light years from the Earth, so it takes like 83 years to come or to leave those stars and make it to our telescope, where it ends its journey tonight. And there are different components. So the Zeta Cancri system contains two binary pairs, Zeta 1 Cancri and Zeta 2 Cancri. And each of Zeta 1 Cancri and Zeta 2 Cancri are binary pairs. So there's like two binary pairs over here, or there's a binary pair over here, blocking out that, there we go. Binary pair over here and a binary pair over here. They're orbiting around their common center of mass, and both pairs are orbiting around a common center of mass. So yeah, having a lesson on gravity and orbits, which my students will be getting tomorrow, will help, and I will use this as an example. So the two binary stars orbit their common center of mass every 1,100 years. Zeta Cancri can be resolved as a double star in small telescopes. Its double nature was discovered in 1756 by Johann Tobias Mayer. William Herschel, the famous William Herschel, who discovered so many things, who spent, I think, his entire life with his eyeball right up to an eyepiece. William Herschel resolved the two components that make up Zeta 1 Cancri in 1781, which is the same year that Uranus was discovered. As early as 1831, John Herschel noticed perturbations in Zeta 2 Cancri's orbit around Zeta 1 Cancri. And then that perturbation in its orbital path led them to believe that there may be a gravitational influence of another object. And that was when they discovered they postulated the fourth unseen component, which closely orbited the visible component of Zeta 2 Cancri. So Zeta Cancri is Zeta 1 Cancri, which ends up being two stars, and Zeta 2 Cancri, which ends up being two stars, which is very exciting. So there are 4 stars in this system. It is a quadruple star system, but visually I think we are only going to be able to see 3 of them. I think we've got Zeta 1 Cancri, Zeta 2 Cancri, and then probably the 2 components of Zeta 1 Cancri. I have never seen Zeta Cancri through a telescope before. This is actually kind of exciting. I've seen many things through telescopes. This is going to be fun.
Are you on the attic view right now?
I am heading to the attic view now. Yep.
We're just centering, and we're going to see if we can focus this a bit better.
All right, so we've got 2 golden colored stars that are being zoomed in on.
I'm trying to split the big one.
Sorry?
I think we're trying to split the big one.
So the brighter of the 2 is what we are going to see if we can't resolve the 2 components. So each of those 2 stars, the one that's a little brighter and on the upper left, and then the one that's a little dimmer on the lower right. Oh, there we go.
Good call.
Look at that. Every so often, when the atmosphere stabilizes for a split second, that's when you can see the 2 stars. So each of these 2 blobs of light is in fact a 2-star system. They're binary systems. They're 2 binary systems we're looking at. But this is a little tricky. As you can tell, they seem to be dancing around, which again is caused by the atmospheric disturbance, the Earth's atmosphere, not the star's atmosphere. Stars do have atmospheres. They have different layers of atmosphere, just like the Earth has different layers of atmosphere. The troposphere and the ionosphere and the other spheres.
Do we know the separation of those 2?
Yeah, so the components of Zeta 1 Cancri orbit each other every 59.3 years.
I was just wondering if it. Oh, yeah. So the separation between C and D is 0.3 arc seconds. Okay. Not tonight.
Yeah, so between A and B,
0.7, yeah.
between A and B. Okay, so between the two main light areas, the two binary systems, it's 5 arc seconds apart. So they're 60 arc seconds in an arc minute. There are 60 arc minutes in a degree of arc. So each arc second is 1/3600th of a degree. And we're looking at a separation of 5 arc seconds between the two between the two binary systems. And then the binary system, the brighter of the two binary systems is, I'm trying to figure out what the separation is, because we can see it every once in a while. Do you think they have that information handy? No, they've got the right ascension, they've got the declination, they've got the,
I'm on the same computer.
wow. Components of Zeta 1 Cancri are denoted Zeta 1 Cancri A and Zeta 1 Cancri B. They both yellow-white main sequence stars of spectral class F. Their apparent magnitudes are blah, 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 blah. As of 2005, they were separated by 0.8 arc seconds. So we have sub-arc second resolution tonight, which is actually pretty good.
Well, I think we have it for moments.
We have it momentarily. But, I mean, those two, I mean, they're 5 arc seconds apart, and, you know, compared to my little homemade telescope at home, this is awesome. So, yeah. So the two components of the brighter, which is Zeta 1 Cancri, they orbit each other every 59.3 years. And then the two components of Zeta 2 Cancri, they orbit, they're closer to one another. So they are going to be orbiting more quickly, according to Kepler's third law. If you're closer in, you're going to be orbiting more quickly. And they orbit every 17 years. So.
By the way, they are G-type stars.
Oh, G-type stars in Zeta 2 Cancri? They are. They are G5 stars. G5 and a G0. So one's a little more massive and a little hotter than the sun. That'd be a G0. And the other one is a little less massive, a little cooler than the sun. That'd be a G5. Which means that if there's planets orbiting those stars, and we don't know that there might be, although we may have seen evidence if there was. But can you imagine? That would be so cool. You'd have like a second sun, not quite so bright as the first in your sky. That's really neat. Tatooine, they always refer back to Tatooine.
Okay, well, this one says they're 1 arc second apart.
1 arc second apart.
6 arc seconds and 1 arc second.
Yeah. That's pretty. I did see them. I did see the brighter one separate into two components for a split second. So, yeah, we can say we saw it. It does look like they're dancing.
Twinkle, twinkle, little star.
Twinkle, twinkle, yeah.
Or twinkle, twinkle, little stars.
Twinkle, twinkle, all the stars?
Next, right.
Have we wonder what you are?
Yes.
No, that's grammatically not appropriate.
Either we could do Iota Cancri, which is another double, or we could do.
It's got about 25 minutes left, gentlemen.
Intergalactic Wanderer.
Oh, the Intergalactic Wanderer is exciting.
Or the M81, M82.
If we can go for a galaxy, hey guys, do you guys want to see a galaxy
Maybe.
out there in YouTube land?
Lower your expectations.
We could try for a galaxy, whoa.
We're trying 81.
blind you guys. I think trying for a galaxy would be fun.
They're close to each other. We can do 2 galaxies.
We can do two galaxies.
M81 and M82.
Of course.
M81 and M82, known as Bodes Nebula and Bodes Nebula. Bode, apparently, was the person. I don't know if it's Johann Bode. He was the man. Discovered, okay, M81 is a galaxy in the constellation Ursa Major, the Big Bear. The stars of the Big Dipper are among the stars of Ursa Major. One of the most conspicuous spiral galaxies in the sky. It forms a physical pair with its neighbor, M82, and is the dominant galaxy in the M81 group. Discovered along with M82 by Johann Bode, and sometimes referred to as Bodes Nebula, because back in when it was discovered, and they're not giving a discovery date, back when it was discovered in 1774, they didn't know galaxies existed. They thought everything was part of the Milky Way, or the Milky Way was the universe, and they didn't even contemplate that there could be galaxies beyond the confines of the Milky Way. So they called it a nebula. It was this weird spiral nebula. M81 is one of the easiest and most rewarding galaxies for amateur astronomers in the Northern Hemisphere. Yay! That's you guys tonight. You're the amateur astronomers. So let's go and see what M81 looks like. Now I'm going to do this through Stellarium. So let's go for our view of Stellarium. That is still looking at the Clownface Nebula, but I am going to type in here. Let me try M81. Now M81, whoa, excessive zoom. Okay, let's zoom out a little bit, and I will show you, whoa, too much out. Oh my gosh. So, we are, this is for our location, the latitude and longitude of Mount Wilson, and then this is the universe. Where are we? I'm not sure where it says we are. Just grab Glendale, California, just to be sure. There we go. Okay. So, this is Stellarium again. It's a free package if you want to download it. I think if you want it on your mobile device, it's $10 or $9.99 or something. But I really prefer the desktop version. You can get it for Windows, you can get it for Mac, you can get it for Linux, and it's really powerful. So if we look southwest, we can see Betelgeuse and the 3 stars of Orion, and then Orion Nebula below the belt. But if we turn ourselves around physically and within Stellarium to look north, if you go pretty much due north and a little to the east, you will see Ursa Major. Now the stars of the Big Dipper are these 7 stars here. But I guess just to the west, I guess, of Ursa Major.
You might want to show them the telescope because
Whoa, we have that. But yeah, Chris is right. Have a look at the telescope. Let me move
Show you
over
where
to
we're-
the dome view.
a rather different location.
Yeah, so now we've totally moved the telescope around, and it's pointing pretty much due north, just a little bit east of north, because I showed you where it was in Stellarium. So this is how the telescope moves. The dome has kind of a window in it. There's a door that kind of opens up, and there's kind of a slit in the dome, and the dome has to physically be rotated to account for where the telescope is pointing. You don't want to open it up wide, because then you are exposed to all the elements, And a little bit of a breeze when it's this cold, not very much fun. So it's 6 degrees centigrade down here, 43 Fahrenheit, which doesn't sound so bad, but usually if you're out in temperatures like that, you're moving around. If you're just sitting on a chair, it's pretty chilly. So, off go the lights. And I'm gonna go back to Stellarium just for a minute so we can zoom in to M81. There we go. So you can see a couple of other galaxies here. And the Stellarium software is interesting because you can actually see, I don't know how well this comes through on YouTube, but you can actually see that there is a photograph here. So this is a real photograph that was taken. A lot of it is just within the software package digitally positioned stars that are accurate for brightness as well as position. But when you have something as cool as M81 like this, then they actually take a real photograph and put that in there. So as you can see, Bodes Galaxy, Bodes Nebula, the Great Spiral, all the different catalog numbers and various parameters about it. Now how are we doing? Are we ready to go over to the attic view? The attic camera, or you're still futzing with stuff?
Galaxy.
We'll just hang out here, look at this really pretty galaxy. So this is, let's have a look and see what it says about this galaxy. So surface brightness, 13 magnitude, 13th place, so to speak, in brightness. It is not something you can see without some substantial light gathering power. So a nice big telescope. And we have sidereal time, circumpolar, parallactic ancel size, that's angular size, orientation, distance. So we have something that is 3.6 million parsecs away, or I'm going to round this up to 12 million light years. 12 million light years away. That's pretty astounding. I'm just going to pause time here so the Earth doesn't rotate, and then we don't see the galaxy seem to shift off to one side, which if I allow time to continue, the motion that you're seeing, not the galaxy, it's the Earth rotating. So I'm just going to pause the Earth's rotation within the Stellarium package because I can, and then point out areas of this kind of purplish reddish. Those are going to be huge nebulae of hydrogen gas. So you can see the hydrogen gas glowing, and also the dust. So I've talked about dust before. The dust will absorb light from what's behind it, so you can see these dust lanes through the galaxy. And often it's a combination of the spiral arms, which are areas of a lot of star formation, so they're nice and bright, and then the dust lanes that give this characteristic kind of spiral feature to many galaxies and give it kind of a little bit of depth and beauty.
You can go to the attic.
I'm gonna go to the attic. All right.
What's in with the
I need to. I'm getting better at this. Okay, attic view. Boom. Okay. Not as impressive as Stellarium, but it's the real time
We're also going
now.
to pin up as soon as we're done.
Yeah, so, yeah, we have to kind of massage. If you look at the bar at the bottom, there's a black line here and a white line, and these are kind of the extremes for what you're looking at, and you want to try and have them on either side of this peak, which is going to be the light output here. So you'll see Chris manipulate the positions of those two lines so that we can bin thing, get a better light exposure. Is it being difficult?
Sometimes the software, I just don't understand.
We've had software issues. I had to restart Stellarium. It's
Try 6
just,
seconds.
you can take a minute wherever you are out there in YouTube land. Go grab yourself a cup of tea. There's always copious amounts of tea and hot chocolate consumed during observing sessions. Coffee occasionally, but not by me. That'll just keep me up, and I've gotta get up and teach in the morning.
Second. Let's try dividing by 4. You do it now. Oh my goodness.
Ah, what you can't see is Chris getting extraordinarily frustrated and
Just not doing what I'm asking it to do. All right,
making
well,
hand gestures towards
try
the
going back to
monitor.
the preview instead. All right, being to okay, let's try that. It just does not want to bin. Oh well. That's
It
the
is
view.
not
That's what
binning
we get.
tonight. That's super disappointing.
So-
What you're looking at is the very central region. So if we go flip to Stellarium for a minute, it'd be this region right in the center. So these other areas that are a little farther out are going to be
Is that number?
much lower, obviously in brightness, a higher magnitude value, and
There it is.
yeah, that's what we got. Oh, now there's a bright something over to the left-hand side in the attic image. I'm going to see if there's anything in Stellarium we can.
I'm guessing
Oh, I
it's
don't know.
star.
Star.
Yeah, it's probably a foreground star. So these things that look like stars in Stellarium, they're going to be part of the real photograph that Stellarium imported into its software. But these things here, they're going to be foreground stars, stars in our own Milky Way.
You don't even have dark exposure.
So just like when you look out your window and you're looking at something in the distance, like a house down at the end of the street or an apartment building or whatever, there could be things between you and that distant building, leaves, for example, or bushes or things. Some things that you can see through, like especially these days, you know, my trees on my road don't have too many leaves.
Right.
But there are a couple of them, so you can definitely see through the trees, so to speak.
Might as well.
But what are we looking at?
So this is M82, which is a regular spiral galaxy.
Yes.
81. And now we're going to go to M82, which is like close by,
Yep.
just to see the difference.
Okay, so this is M81, and now we're going to hop over to M82, which is very exciting.
Let's zoom in so we don't give away the
Location.
no give away the.
Don't give away location.
All right, so we're bringing over Richard's view. Damn it! What did I do? Did I do this?
Just go like that.
Okay.
So we're going from the 60-inch telescope view to the 5-inch telescope view. And I think you can actually see that pretty well.
Is that?
Yeah.
Did that do? Oh, it is doing. Okay.
Yeah. So you can see some nebulosity, some of the structure. I don't know. You know, sometimes you're like, yeah, I can see that. And you're like totally lying to yourself. But
So
I
once
think I can
again,
sort of see it.
To compare, what we're looking at with the 60-inch is something more like this.
Yeah. So the 60-inch has a very narrow field of view. You're really zoomed in.
But with that, you also get color.
Well, yeah. We get color with the 60-inch. There's some trade-offs.
Are we going? Whoops. Oh, don't want to lose this. Bring that back.
Do you want to pull that over a little bit, Chris, so that everyone can see kind of the controls? Because sometimes seeing the controls is kind of neat.
Okay. I
So the-
purposely actually crop them out, but
Yeah, but if you want to see what's going on,
Yeah,
I mean, they don't
so-
have to control everything, but they can see you kind of control. The exposure time is the very top parameter that can be changed. And then we have binning.
which it's currently ignoring.
Yeah, that
You
software
want to
is
explain what binning is?
being difficult. No, I don't know.
Takes neighboring pixels and averages them together.
Yeah, basically, you've got a whole bunch of buckets out there, and it's raining into all the buckets, and the binning is when you decide to take 4 buckets and dump them into one. Something like that. They've been hanging out with us for an hour, almost 2 hours, and their brains are full. They're like, I have to learn more? Nuh-uh.
It's there, it's filling the field.
We have 10 minutes left, folks.
All right, so
And by the way, for my students, you don't have to come for the whole 2 hours. You know that, right? You would just come for a little bit. Unless this is your star party. So if you're coming for the actual star party assignment, yeah, you can stick it for another 10 minutes. Stick it out.
I really wish it was bin though. That's so disappointing.
Oh, yes. Software issues.
I'm gonna do a 15-second exposure, but you can go to the attic if you want, or you are on the attic.
I'm on the attic. Yes.
So this galaxy, unlike the other one, is kind of edge on. And it's a starburst galaxy.
Ooh, M82 is.
M82 is a starburst. And it also has an active galactic nucleus.
Oh, AGN's active galactic nuclei.
Oh, that's what Tom said, does it, or does it not?
M82 does not. It's a
Does not.
starburst.
Sorry, scratch that. It's just a star. It's
It
just
has
a
a,
starburst.
it has a massive superwind being driven by a starburst, so it's really interesting.
Okay, no AGNs. We lie.
But it has a galactic superwind.
Galactic superwind?
Yeah.
That sounds rude. That's awesome.
And these
You know,
parts
even
here that-
astronomers can't say the
and it
name of
almost
the
looks like there's
seventh planet with a straight face.
where it looks like it's missing light. That's actually, I think, dust
Yeah.
in the plane. So that's the same reason that we have gaps in our own Milky Way on the sky. You're seeing the same sort of thing here, these gaps, but there are stars there, it's just that they are behind some obscuring dust.
So, for people out there, what we're looking at here is the very so this is the attic camera view, which is the very zoomed in version. And if we go to Stellarium, I'll show you what that looks like here. So this is the
Actually-
image from Stellarium.
I was just going to say, we can go to Richard's view, because I think it's going to be just as good.
And then zoom in a little bit here. So all of this dust lane, like all of this dust that we're seeing here, that's probably what we're seeing when we're looking at this here. So you're seeing, we want to take exposures that are longer and then stack the exposures so we have more light gathering ability. But right now, the software package that controls the cameras just basically saying, nope, I don't want to. So,
Wow, it actually made quite a difference.
trials and tribulations. Wow, what just happened? We lost most of it.
Well, so Tom turned off the red lights in the dome.
Oh,
Red lights in the dome. So try to reduce
Oh.
our background light.
yeah, so we have some lights on in the planetarium, or sorry, in the dome. Let me just turn off this red light as well.
I can remember that one right now.
And if we turn off some of the ambient light here in the observatory dome, then it can't be picked up by the telescope, and our camera's very sensitive. So, I mean, as you saw, the telescope isn't a solid tube. It's kind of a framework. We don't want it solid because we do want things to cool down. Like, we want the mirror to be at ambient temperatures. So we just have this structural framework.
Okay, we're going to bring Richard's view over.
Ooh, Richard's view. Okay.
Because, ta-da, you can see both at the same time.
That's lovely. So this one over here is M81. And we have dueling mice and mouses, M82.
You may choose over here.
I'll take my mouse away and you can. That's pretty. That's really pretty.
Colors are gorgeous.
The colors are stunning. And I think this may be a good place to end the evening.
Well, I was just thinking, we're very close to the 9:30.
Yeah,
check to see
we're
if there's any
close to our
remaining
9:30
questions.
cutoff. Sorry, what was that?
Check to see if there's any remaining questions.
Any final questions? So I can tell you that this galaxy, discovered in 1774, is dum, 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 dum. How far away is it? Come on. Physical properties. It is 38,000 light years. Oh no, that's the diameter, 38,000 light years. Where's the distance?
So 12 million light years.
12 million. Okay, so they're both about the same distance away from us. And they are interacting gravitationally.
Which is probably
Like us in
driving the
Andromeda.
starburst. Yeah, so
Yeah.
the gravity from one is disturbing the other, that compresses the gases, that causes stars to form, and that's why you get this star forming.
Awesome.
Jeff, who is with us, is more of an expert about these things. I know about stars that blow up. I mean, I don't know so much about the galaxies they live in.
This is one of my favorite galaxies because it's the prototypical starburst galaxy that's really close to us. So astronomers love to study it because it's right in our backyard and it's got a massive, it's forming stars at 10 times the rate of the Milky Way,
Wow.
just banging them out. And that's driving gas and dust out of the galaxy. It's making so many stars so quickly that it's just going crazy and blowing gas out. You can't see it in this telescope view, but in the beautiful image that we saw in Stellarium,
Yeah.
that red light is
Yeah.
hydrogen gas. It's really cool.
Yeah.
There it is. There it is.
There it is. Yeah. All right. Well, thank you very much for joining us this evening. I'm glad you guys had fun. We are definitely trying to stay warm up here. We'll definitely be warmer as soon as we get in the car and crank the heater for our drive down the mountain. But I am going to finish things up tonight. I'm just going to come back over here so you can see a little bit of me. My warm little balaclava. But thank you so much for joining us this evening. We've had fun up here. See you again in 2 weeks. If you want to come join us again in 2 weeks, we will have some similar objects and maybe some other surprises to view as well. So I will say good night.
Done.
Yay! Done.